So, welcome back to the Neuro Symbolic Channel. This video is actually a little bit of a compilation of a bunch of lectures dealing with large language models. And the way it'll proceed, we'll start with a lesson on embeddings, which is how language is taken from text and transformed into a vector representation. And then we'll cover the transformer architecture to kind of get the basics on that. And that will be followed by two lessons where first we'll go over the encoder architecture, which deals with the BERT models, which will be followed by a lecture on the decoder architecture. And this is things like the large language models and GPT, what's called generative AI. And then from there, we go into two lectures of prompt engineering, and we wrap it up with a short lesson on hallucinations and the limitations of large language models. So this is designed to be a somewhat gentle introduction to the subject. This is not meant to be, a thoroughly technical, in-depth series of lectures, but it does assume that you know at least a little bit of the basics of deep learning and machine learning. So if you're totally new to the subject, it might be a bit much to start with this. We have other videos on the channel that are more, if you're just coming to this totally from scratch. So anyway, with that in mind, I really hope you enjoy this series of lectures. Thank you very much.
Welcome back. In this lecture, we will discuss embeddings, which is an important concept to understand how RNNs can be used in language translation or other language classification use cases. And so here are the objectives. So in an earlier lecture, we talked about some key challenges with RNNs, and right now, we're going to focus on the third of those, which is how do you perform an initial encoding when the data is not a vector, because text is not a vector. So, as we've been saying all along, a major motivating use case for RNNs is to reason about natural language. And earlier when we talked about architectures, we said, hey, here's your X vector, it's a word. Well, to some of you that might have seemed kind of weird because our language is, not made up of numbers. It's language, it's made up of letters and stuff. So, how do we bridge that gap? Because neural networks are designed to be used on vector representations of things and not words. So let's talk about that. One technique that's widely popular is what's called a one-hot embedding. So here you have a dictionary of all possible words, so we'll just say n number of words. And for each word, you have an n-sized vector where the position of that word is 1 and all the others are 0. So let's take a look at an example here. So let's say this is our dictionary. We just have a couple of different pet types: cat, dog, fish, turtle, and snake. And so that's 5 words in the dictionary, so these will be vectors of size 5. And here's what the vectors look like. All we're doing is this, the 1 is just in a different location for each of the different words. And that's how you transform the words into vectors using a one-hot embedding. Now, this is a very simple way of doing business. We could also look at learned embeddings, which is more sophisticated. And so the concept is take words in the dictionary and embed them in some kind of lower dimensional space, maybe with another machine learning technique. And the advantage here is you can actually have smaller vectors, and you could have similar words be closer together within that vector space, which is a nice byproduct out of this as well. Now, there's a whole area within machine learning called representation learning, and that is the study of finding clever ways to do this embedding. So that's it for the lecture on embeddings. Stay tuned for more content. Welcome back. In this lecture we will discuss the transformer architecture. This uses what's called an attention mechanism, and it's a neural architecture that's used in the very popular BERT models that some of you may have heard about. Also note, even though this lecture might be in a block about, quote, recurrent neural networks, the transformer architecture is not a recurrent neural network, but rather an alternative to it. So here's our objective. So let's go back to the challenges with recurrent neural networks. So even sophisticated RNNs such as long short-term memory, the long-term memory is limited for very long sequences of information. Also, the relationship, this hidden state that we had among cells, prohibits parallelization in training. So the cells are dependent on each other. And we also had this question about how to perform the initial embeddings. And while that's not the primary challenge addressed by the transformer architecture, the embeddings are different compared to the standard RNN setup. So here's some of the key ideas. So one, let's get rid of this recurrence relation. We can't parallelize it. Let's just kind of be done with it. And two is let's capture this idea of the position in the embedding itself. And this is like really interesting because we are now able to talk about the different inputs in relation to each other based on the inputs themselves. And you'll see why a little later. This is kind of a really neat idea. This idea of attention weighting is a way of weighting similarity between items in a sequence. And now let's just dive right into the architecture. So, okay, we have this positionally aware encoding of the sequence data. And so we have all of these vectors for everything in the sequence, and each vector is a concatenation of the input and its position in a single embedding. We take that and we repeat it 3 times. And with each time it's repeated in this first layer, it's going into a neural layer or a series of neural layers depending on the architecture. And one is for what's called the key, the other is called the value, and the third is for the query. So what happens, so those neural layers are giving you those 3 what we call transformations of the input. So you have 3 different transformations of the input. Now the first 2 of them, we're going to do a similarity comparison. So pairwise similarity between the inputs, between the key and the value. And so this is, the result of this is what's called attention weighting, and this is your key value matrix. And so there's some scaling, and also normally there's softmax that's at the end of the series of layers that do attention weighting. We've not included it in this particular diagram. Now the attention weighting is then combined with the transformation of the query in another neural layer that provides you the output. Now what's interesting here is the positional relationships between the different inputs, how important those relationships are to each other really starts to fall out in the similarity matrix. And that's what's kind of neat about the whole thing, because it's taking care of the positional encoding along with looking at specifically what needs to be related to what in the input through this concept of attention weighting, through this similarity matrix. Everything here is a regular neural network. There's none of this hidden state stuff that's between layers, and this is much more easy to parallelize than your traditional RNN architecture. Oh, and one other piece, what we showed here is what's called a self-attention head. And this is the neural unit of a transformer architecture, and we can have many of these units for different things if we want. So some considerations is pros, big thing here, easy to parallelize, captures long-range dependencies. Really famous example of this is the AlphaFold 2 transformer-based model created by Google DeepMind. Solved the protein folding problem with very high accuracy. And that leveraged the transformer architecture, and the reason why it performs so well, even outperforming previous neural networks created by DeepMind and others, was due to the ability to capture these long-range dependencies because of the transformer architecture. Now, probably the biggest downside of transformer architecture is it involves a quadratic operation because of this similarity matrix. You're comparing all the inputs with itself, essentially, and that's a quadratic computation. Now, in practice, this doesn't turn out to be such a big deal because of the ability to parallelize, especially through GPUs. But bear in mind, we wouldn't want the sequence to be unruly lengthy, because that would lead to very expensive computation in the attention weighting. So that concludes the lecture for the transformer architecture. Hope you enjoy the rest of your day. Welcome back. In this lecture, we shall explore encoders with a specific focus on the BERT models. So here are our lesson objectives. So earlier we described what's called the self-attention head, which is shown here, and this is the key neural unit that is used in what's called the transformer architecture. So as you may recall, we take the input and it goes three different ways into keys, values, and queries. The keys and values are assembled using attention weighting, and then the query is then compared to that to give you the output. Now this itself becomes the basic building block of what we call the encoder architecture that I'll describe next. So the encoder architecture is primarily used for things like assigning a label to textual data, sentiment analysis, a lot of the typical, what we would call earlier, a many-to-one task that you would see in other language models like an RNN. Now, this involves encoding textual input into the neural architecture to produce the output, and we'll describe how that's done in a moment. So at the base level, we have the input. So these are your words. Now, if you recall, when we talked about transformers, words not only have an embedding, but positional information is included in that embedding. And by doing this, by including the positional information in the embedding, remember, this is what allows us to parallelize things, because we don't have this kind of series of neural units, one feeding into the other, that you have with an RNN. So that positional information is then combined with the initial input to give you positional embeddings. Now notice each of these embeddings, we have three arrows coming from it because we're going into the three different parts of the transformer architecture, which we see here, and that's the next layer in an encoder. Now the output of the transformer is then pushed through a dense layer. And then there's some normalization, some other things that are occurring on top of this prior to the output. Now typically all this together, with the exception of the embeddings, get stacked on top of one another, and we can have multiple encoder units. So the combination of the attention head and these dense layers with the normalization on top, those things together comprise an encoder, and you can stack multiple of those on top of each other, and that's what's often done. So the BERT model is a very popular pre-trained encoder transformer model. It was created by Google, but it is available open source. And it's pre-trained on two tasks. It's trained on what's called masked word prediction, where you have an input sentence and about 15% of that input is masked. And then what it's predicting is the missing words. The other thing is what's called next sentence prediction. That's actually taking two sentences as input and concluding if they belong to the same context. Now, this type of pre-training on these two tasks uses something called self-supervised learning, which allows the model to be trained on a lot of data, but not relying on a lot of labeling. And we'll touch on self-supervised training in a bit. Now, what happens is you have all this stuff that's pre-trained, and this is somewhere in the neighborhood of like 100 million parameters or so. So it's a big model, but it's small enough where you can still download it and use it yourself. Now, what you want to do is you want to do what's called fine-tuning, which is adapting this model for other tasks by doing things like integrating it in a larger architecture, adding additional layers, and so forth, usually a bunch of dense layers on top of that for a specific classification test. And the BERT models and its later variants have shown to be very effective when used in this way. Now let's talk a little bit about the self-supervised training. So when we have these neural models, they can get very large. And the larger the model you have, the more data you need to learn the weights within the model. Now, if you can't, unfortunately, you can't just arbitrarily grab more and more data, because in the supervised case, we, as you know from earlier lectures, expect labels with all of those samples. But when you start getting into very large amounts of data, internet scale data, labeling no longer becomes practical. So we have to think of something else. So this idea of self-supervised learning is saying, hey, we got this textual data. If we mask part of it, or if we arrange it in a certain way, we can draw conclusions from that without relying on labeling. So this idea of masking, which is one of the things done with the BERT model, is you might have something like this sentence: in the morning, I brush and floss my teeth. And then maybe the word teeth gets masked out. And so based on the beginning part of that sentence, what is that final word? And as you see right there, we can all guess as humans that with that particular sentence, if you hear in the morning I brush and floss my blank, most of us are going to likely fill in teeth with a very high probability. Essentially, we're getting the model to do the same thing. BERT has been very successfully deployed for many years now. One of the main applications has been improvements in Google search. Google has said that this was one of the biggest leaps forward in the history of search at the time of its release in 2018-2019 timeframe. It's open source and free to download, so if you're interested, the Google version for TensorFlow is available. Google is also the company that makes TensorFlow. However, there are PyTorch variants, and Meta is the company that makes PyTorch. You can get the PyTorch version also for free in a package called PyTorch Transformer. It's a relatively small model compared to some of the more recent large models we've seen, like the GPT series things that have billions of parameters. Here we're dealing with a 336 million parameter for what's called the large BERT model at the time of this recording. And so as a result, you can fine tune on commodity GPU hardware. So that wraps it up for encoders. Hope you enjoyed the lesson. This is a very exciting area, and a lot of good results have been gotten out of this, and we think it'll benefit you in your work. Thank you. Welcome back. In this lecture, we'll explore what is now being referred to as generative AI. That primarily revolves around something called the Decoder, which is another framework that's built on the transformer architecture. and in particular the instantiation in the GPT models, which are a well-known large language model created by a company called OpenAI. So here are our lesson objectives. All right, so earlier we talked about an encoding model such as BERT. And in this case, you have a pre-trained model like BERT, and you have a specific task you want to adapt it to. So you take that pre-trained model and you add some extra layers, you do your gradient descent, you learn the weights for those layers, and you apply it to the application in that way. Now, here's the issue. You still end up needing a whole bunch of labeled data for your target task. The other thing about it is every time you do that, you're making a new model, and those models are very specific for that task. They're not general, which is okay for a given task, but if somehow your task changes down the line, you have to go back, retrain the model with the new weights and so on. There's also some evidence in the scientific literature that this approach results in overfitting during the process of learning those additional weights. And that process, again, is called fine-tuning. So how do we get around this? Well, let's take a step back and look at another result in which the size of the model is compared to the test set. And when we look at things like compute, data set size, and number of parameters, all those things are directly related to how well the model performs. So as we see the loss in a test set with these very large neural approaches gets lower and lower just by throwing more data and more parameters at the problem. And the study that showed this illustrated that these factors are much more closely related to the accuracy of the model as opposed to other things such as the architecture. Now, can we use this idea to maybe create a more generalized model and somehow get away from this fine-tuning process that, as you saw in the previous slide, leads to things like possible overfitting, having to go through gradient descent multiple times for each use case you have, and so on. And so if we have a very large model, and we're talking models with billions of parameters now, and we train it on a task where it can predict, future words in a sentence or a conversation, can we use this in other things and avoid this fine-tuning process? And the answer is we can. We do it with what's called prompting. And to get a little bit of a glimpse as to how these decoder models differ from the encoder models, consider BERT. Encoder architecture, it uses this bidirectional relationship. So when it masks a word in a sentence, when that is done, it's predicting that word based on both the words that come before and after. And this masking occurs on the input. So it's almost like with that self-supervised process we described, we are essentially turning a regular data set into a label data set where the labels are, in effect, the masked words. GPT, which is a decoder architecture, we're looking at something a little different. Here now we have only unidirectional relationships because we only want to predict the words that are coming in the future. And here the masking is actually integrated into the softmax layer of the attention head. And it's these ideas that lead to generative AI because now we're predicting words that are in the future, not based on anything that we have maybe prior knowledge of what comes after those words, only what comes before. And so let's give an example. Consider this input. We've tokenized this sentence, my dog loves food, and we have a start and end token as well. And then what we want to do is that goes into a decoder. And then the desired output is everything that's one position to the right of it as you read it. So the start token maps to my token maps to dog, and so forth. But it's more than just that token in the input mapping to the corresponding position of the output. The output token can also depend on everything that came prior. So we see that, for example, with dog, we have a dependency coming from both the start token and the my token. By the time we get all the way to food, we have dependencies coming from everything else. Whereas when you look earlier on, my only stems from the start token. So the decoder architecture, when you look at kind of a high-level view, it looks very similar to the encoder architecture. However, the key differences, come up in one, this unidirectional dependency, and two, masking within the attention head. Here, the masking occurs in the attention head in a way to enforce this unidirectional flow of information. So you might hear a lot about what's called a large language model or a foundational model. And this is referring to large models that are trained in this fashion using this decoder framework. GPT in particular, that's OpenAI's LLM. And these things are very expensive to train. They often cost upwards of tens of millions of dollars. And as a result, the expense incurred by training, as well as the sheer size of it, is normally you're not going to access these models in a direct fashion. Rather, you're going to leverage an API. Now, this is a purely black box thing, not only just in the typical way we talk about a neural model being black box in general, and that it's hard to make sense of all these weights, but we also don't know what changes a company like OpenAI is making to the model behind the scenes. If they, did they retrain it the other week? Did they make certain implementation changes that cause it to provide different results for a given input? And, the best you can really hope for is that you'll have updated documentation from the vendor. You don't have that control that you do with something like a BERT model. But the trade-off is we can use this model in a way that avoids fine-tuning, which is actually quite powerful. So that's the introduction to the decoder architecture. Stay tuned and we'll explore more topics related to this soon. Welcome back. In this lecture, we will introduce prompt engineering. So here are the lesson objectives. So earlier we described the decoder framework, which allowed us to adapt the model to a specific task and avoiding the fine-tuning process, having to learn additional weights using gradient descent. And so the idea here, the main idea behind prompt engineering is that the model is initially trained using what's called in-context learning, where there were aspects of the context of the training samples included with that. And because it's been trained in this way, you can prompt the model using natural language to get a result. And you can do things in that prompt that can be task specific. Thereby, you can adapt the model to a domain-specific task without having to rely on the fine-tuning process. So in everything we talk about now, we're adapting the model to a use case, but the weights stay the same. So prompt engineering is all about designing a prompt for one of these models around a specific task And the key elements include instruction, context, input data, and the output indicator. So let's give you an example, and this is actual results from ChatGPT. And here the instruction is identify the distance to the location in the input. And the context is that the current location, let's say, is Tempe, Arizona. And the input is we went to Prescott and San Diego for a vacation last year, and the output is distance in miles. And you see ChatGPT returns this nice English language result that is correct, by the way, where it pulls out the two locations in that sentence, Prescott and San Diego, and it gives you the amount of miles to each from Tempe. Another variant of this that is actually really important to know is that the output format doesn't have to be natural language. It could be something that's highly formatted, such as a programming language, or as in this case, we have JSON. This is important because if you're using ChatGPT or some other large language model through an API, chances are you want to further process the results of that input. Producing results in something like JSON can help you do just that. So common use cases that we've seen to date have been things like text summarization, information extraction, question answering, and so forth. Zero-shot prompting. Here, we deal with giving instructions in an input, and an output, we're asking for the result of that. And zero-shot prompting, there's not any examples of what a previous instance of this would look like. But we rely on the fact that the model is so large and trained with so much data that it can just give the right result. And here we see in the task is effectively sentiment analysis. And the input is, I was angry with the test result. And the output, we say positive, negative, or neutral. And the large language model successfully returns negative. And it makes sense. The statement is, I was angry with the result. Now, consider this example, though. Let's say the input is, I was XYZ with the test result. Now, XYZ, of course, is not a word. And since it doesn't know the definition of the word, it just says neutral. But this is actually a failure mode because what it should say is, I can't answer it because XYZ cannot be defined. Now, of course, you can adjust the prompt to kind of tease that out a little bit. But what the real failure here is that there was not enough information to give an accurate answer. So in this case, we want to go with something called few-shot learning, where we take XYZ and we maybe give some examples on where XYZ was positive or negative. And so here we give an instruction, and now our context is a set of examples, and this kind of format is very typically seen with these large language models. And now we have a sentence and the associated label. So it's like we're doing a mini version of supervised learning for the model. But it's not really training it on the data. What's really going on here is it's setting the context. It's kind of adjusting the earlier textual input in order for the transformer architecture to identify something that falls within a probability distribution of the next word that is more in tune with the overall input text. And here are those examples. So that's our introduction to prompt engineering. Stay tuned because we'll continue this discussion further. Welcome back. In this lecture, we will continue our discussion on prompt engineering. So here are the objectives. All right, so earlier we described zero-shot and few-shot prompting, and we have two examples. The first one we have as input saying, I was XYZ with the test results, and we asked the LLM to classify the sentiment as positive, negative, or neutral. It says neutral, likely because It has no context of what XYZ means. In the second example, we added a few examples of XYZ being used in context. And so as a result, the model was successfully able to conclude that the sentiment was negative on the input. So why does this work? Well, the samples, they are really adding more context to the model. They're adding a bunch of text at the beginning that's building up on the relationships that are expected to see in the output. And then if you recall in earlier lectures, we discussed how these large language models are essentially next word generators, but they're doing so probabilistically. And we could think of this initial context as adjusting that probability of what word gets predicted next. And so let's revisit an earlier example we showed on the relationship between the input and output of a large language model. The dependency structure is unidirectional because we're following a decoder architecture. And so we see like the word dog, it depends on predicting that word both on the initial token and the current token, which is my. So basically, knowing that the sentence began with the word my, the next word is going to be dog. Now, building on that, let's look at the probability distribution of these words. And I just made these up to illustrate the example. So let's say, for example, that my, the model picks that with a probability of 25%. It could have picked the, maybe with a higher probability. Now, knowing that that was how the first word was picked, we are now picking the word dog, which is we're looking at the probability of the next word. But notice the first time we were conditioning on only the start character. So here we could think of as, in this simple example, as a big probability distribution over all words you'd commonly start a sentence with. Here, we're looking at condition on two things, the start token and the word my. Building further, now that we know dog, we can condition the next word. And you're probably going to see in a sentence like this that the PDF of words at this point, because the first word is my, the second word is dog, it's likely the third word is going to be some kind of verb, just as the second word was very likely to be some kind of noun. But that is simply because it's conditioned on a different set of words than the second word was. And so we see this as it goes through, we have these probability distributions. Now there's kind of two things to note here is this conditional here that we have been talking a lot about. If I add a bunch of extra text at the prompt, I'm changing what that conditional probability is conditioned on. So that's why having these extra examples are such an effective way in doing few-shot learning. On top of that, notice that we have a probability distribution over the word that gets picked next. Later in the lecture, we'll also discuss ways to modify how the language model selects from that probability distribution. And that's what we got here. So temperature. So when the model selects a word, it's selecting probabilistically. So if the word is going, whether that first word is going to be my or the, it's flipping a weighted coin to pick between them. So if it was the word A with a probability of 0.25, my with a probability of 0.25, and the with a probability of 0.5, it's going to pick one of those three based on those associated probabilities. Now, if we adjust the temperature, if it's a low temperature, this makes it more likely that those high probability words will get picked, and there's going to be less randomness in the result. If you pick a higher temperature, it's going to increase the probability of words that don't have such a high value being picked. There's also parameters dealing with top K sampling. So this is just limiting the top K words. So you could imagine in the slide I just showed you, you're essentially doing top 3 sampling. We're only limiting the probability distribution to having only 3 things. You can also limit the sampling based on the sum of the probabilities of the top elements as an alternative, and that's called top P sampling. But all 3 of these settings, they are available in most of the major large language models provided by vendors. Now, we talked about different types of prompts earlier on, and we talked about how few-shot learning can really help us with some of our issues. But there is a type of question called reasoning where you have to think through something, think through the result. And you have to understand, as human beings, when we get a question, we reason through the results. We think of things generally in a step-by-step way and have some kind of logic. The large language models, they don't do that. They are mimicking. They are returning an answer based on the series of words only, and they are just predicting what the next word is going to be. There is no underlying logic to that. And so for very simple tasks, such as some of the ones we've had in the slide that are very kind of, surface-oriented, a small number of sentences and stuff like that, we can get really excellent results that make this thing seem like it's very smart. But tasks that it normally fails with are where you start giving it stuff like logical puzzles or things that require step-by-step thinking. Now, in some of our own research here at ASU, we've actually seen this in practice. So what we did was we fed the large language model, ChatGPT in particular, 1,000 math word problems, and we looked at which ones it failed on, and we noticed that when the number of addition and subtraction operations required to solve the word problem increased, the probability of failure increased with that in a very direct relationship, as you see here in the slide. And when you think about an algebra problem, when you take multiple steps in solving that problem, addition and subtraction operations, that's one of the places where your steps tend to get divided up. And this is where failure occurs. So, large language models have trouble reasoning. How can we work around this? Well, one is maybe just avoid multi-step reasoning problems altogether. So if you think about the problem that you're trying to address with a large language model, is it something like a classification problem where you can get a pretty good result just by investigating the input and sort of stamp a label on it? Or does it need you to think through things step by step like a puzzle? If it's the latter, you're probably entering into the world of reasoning. So one easy fix that is surprisingly effective is adding the words, "let's think step by step," to the prompt. And this forces the large language model to kind of describe its output in a step-by-step approach, essentially creating more context for the next step, which will improve the accuracy of the result. And we saw dramatic results in the experiments we had on the last slide when we forced the large language model to show its work on a math problem as opposed to just giving the final answer. Using few-shot learning, where you have similar reasoning problems, has also been shown to help. And this is often called a chain of thought prompting, particularly where the examples have a walkthrough of the solution, where that step-by-step nature is actually in the examples. Another variant of this is to then pick examples where the line of reasoning is different among the examples. And this has also been shown to help with results. Finally, probably one of the best ways to work around the reasoning limitations of a large language model is to just have the large language model generate some kind of code or reformat the input So then you could send it to something else that can solve the problem. And an example of this would be there was a plugin released by a company called Wolfram Alpha, where ChatGPT would take the input that was in natural language and transform it into something structural that would then be used to actually solve the problem by leveraging stuff in Wolfram Alpha's database or use Wolfram Alpha's ability to solve math problems. And so everything that involved reasoning was offloaded to this other piece of software. And you don't have to use Wolfram Alpha to accomplish this. For things like math problems, there's a package called SymPy that can solve math problems. So you can convert the ChatGPT output, use that to send off to something like SymPy. ChatGPT is also very good at automatic code generation. So if you use your textual input to kind of then structure how to solve that problem with a piece of code, maybe then that code can run and actually solve the problem. So this is another way of thinking about these reasoning problems. But the key insight here is that it's really important to recognize that when you're entering into this world of reasoning, because results get much, much worse than in other use cases for the LLM. So other trends in prompt engineering that we've noticed that are interesting. So one is that if in certain use cases where you might want to generate data for training a supervised model, like not using ChatGPT at all, or an LLM rather, is to use the LLM to just make up a set of training data. And it can do this fairly well for a lot of textual tasks. So that's actually a really nice thing. And likewise, you can use this to generate unlabeled data, which is probably will do even better because most of what it's going to produce is going to still have good grammar and spelling and stuff like that. Automatic code generation. This is an emerging use case that there's been a lot of success with, particularly with very small coding requirements. Asking the large language model itself to generate a prompt to answer a question has also been shown to be effective. And then have the model generate knowledge to use as context for the prompt. And we kind of saw examples like this when we talked about reasoning, where saying walk through step by step, that's kind of going down this road of generating knowledge to be used in the prompt. You could think of in a session with a large language model asking it questions about a certain period of history and then using that to preface another prompt that's asking something more specific about an individual person. So for instance, if you want to learn about John Smith and then asking that right off the bat is probably going to not lead to good results because it's a very common name, but then prefacing it in the context of history could give much better results. So that wraps up our second part on prompt engineering. Stay tuned for more content. Welcome back. In this lecture, we will discuss large language model limitations and hallucination. Here are the lesson objectives. So after ChatGPT was released to the public in late 2022 and was used by many people in the ensuing months, a very unfortunate thing happened where someone prompted ChatGPT to tell them about people in academia who were accused of sexual harassment, and it described an incident involving a professor that was totally false. It was totally made up. There was nothing in the news about it or anything like that. And this became a big deal because it highlighted something called hallucination. That's a big problem with these large language models. And so why did the model totally make this up? This seems, really incredulous that this would happen. Well, here's why. When humans are asked a question, we reason through things logically. We think of prior knowledge and we assemble facts together as best we can to answer a question. The large language models are simply predicting the next word in a very sophisticated way. They're mimicking. And because they're so good at mimicking, what they produce looks very convincing when it's presented in natural language. But we have to remember that this is not the same process that we as humans go through when we answer the same question. The underlying process is totally different between man and machine in this case. So why does this occur? Well, fundamentally, the large language model is looking for words that kind of fit together. And if it's prompted with this sexual harassment case with information about academia, sexual harassment, and then it pulls up the next word that has to do with a given academic department in a given school, and then kind of associated with those words is the name of a professor who may be unrelated to the case but related to that department, it just kind of fits the output that the model is providing. So it's okay and it goes with it. And of course, this will likely get worse based on some of the settings that you have, such as temperature. The other thing is the large language model has really no way to check if it's hallucinating or not, because we check the facts by looking at other sources of information, things that are structured, things that are known to be factual. The large language model is not designed to make such considerations in the first place. So there's no way to go and check. The other thing is the data sets these things are trained on are huge, and they'll include fictional data as part of the content. So that kind of stuff can get mixed in there as well. They're also not optimized to refuse to answer to most questions. And so it's very difficult for the model to say, I don't know. Now, granted, they're getting better at this, but in general, they wouldn't be a very useful model if they would over and over again say, I don't have the answer to that. The context of the prompt can also possibly lead to hallucinations. And there has been cases where some of the hallucinations have been reported in the media were created by people who were sort of gaming the large language model by artificially creating prompts to drive it to certain results. So, will hallucinations be solved? And it would be hard for us to solve them as users of this technology if you don't have access and you're not working for one of these firms. But is this problem going to go away? And so, in general, it's likely that we're going to see significant reduction in hallucinations, especially in things that can be confirmed easily. This is an active area of focus, especially for the companies that make these models. They're financially incentivized to address this as much as they can. However, that said, despite the engineering work that these OpenAI and Google and others are doing to reduce this problem, it's not likely that they're going to be able to solve it in all cases. And it's very unlikely that they're going to be able to have the model say it can verify that the answer is correct, at least with the current architectures, because there's no notion of say, fact-checking. There's no structured data to go with that. And the reason why that's going to be tough to do is to have structured data, you have to do a lot more with the data other than push it through the model. Remember, part of the success of being able to train such large models is the ability to avoid labeling all the data and just shoving a bunch of textual data in it, masking it in different ways to come up, with the resulting model. If you are now structuring the data, you are losing the ability to scale to very large data sets. And most of the companies that are addressing these problems, they're using things like reinforcement learning with human feedback and stuff like that to help get around this. And like I said, while I think it's going to improve, it's going to be likely not possible to verify this in the general case. Now, for specific use cases of an LLM, it could be that you can extensively mitigate the problem with hallucinations, partially because if you're dealing with a very specific problem where you've designed prompts and you have access to additional data on the side to verify stuff, you're dealing with a much smaller problem. You maybe have some trusted data. You could even be doing things to limit the scope of the output. And all these facets lead to a much better chance of mitigating the hallucinations and maybe even in some cases eliminating them. However, hallucinations are just one of several limitations of large language models. They are powerful tools, but they are tools, and they're not useful in all cases, and that's why throughout this course we've talked about many different aspects of machine learning. And so, the first, probably biggest one is there's no access to the model. These are models with billions of parameters, hugely expensive to train, and they generally reside behind the locked doors of the companies that make them. So that's a big minus right there. The inability to use the model when not connected to the internet. That's also a serious weakness of these. What happens if you're in an environment where connectivity is reduced or limited? Now you don't have access to your model, whereas if you had just trained something, like we learned in other parts of the course, you could actually put that model on the device and not have to rely on your network. That, of course, is inherently tied to reliance of availability of the vendor itself, making, so if that vendor has any issues where their servers are down, suddenly you can't solve your task anymore. Also, vendors are not really driven to, make all the models work in the exact same way. And so you may have cases where prompts for one LLM made by one company won't work as well on a different LLM from another company. And finally, in general, the results of these large models, it's very difficult to align them to what is desirable for human beings. And this is considered one of the big open problems in artificial intelligence and machine learning today, is referred to as the alignment problem. I believe that for large language models, in the current architectures, this is likely not solvable as is, and we'll need additional technology to address this challenging problem. So that wraps it up for our lecture on limitations and hallucinations in large language models. Thanks for watching.